Okay, so right, so let us finish this proof of Riemann bilinear relations. So I call this the second part, Riemann bilinear relations. That's part two. Yeah, so our setting is, of course, like this. We have X, a compact. We have this X, which is a compact Riemann surface of genus G. And then we consider the singular homology with integral coefficients, which we know is isomorphic to z to the power 2g, is a free abelian group of rank 2g. And I defined intuitively the intersection pairing we had. Intersection pairing. So this goes from H1 xz plus H1 xz to z. And if you want, I use the notation of dot to denote the thing. Some places they just use okay, so the pair A and B is mapped to A dot B, but some books or some places they just use this as the pairing between the two. And basically, intuitively, this, you remember, is the number of intersection points of these two cycles counting with signs. That's what it is. I mean, this needs modification of cycles within the same class. So you put them in general position. So if, for example, if two cycles or do coincide, you can perturb a little bit, and then they don't intersect. So it means that intersection of A dot A is equal to 0. And A dot A is equal to minus B dot A and all these things. So this is basically what it is an alternating, is a skew-symmetric or antisymmetric, basically non-degenerate pairing. So then I showed how to choose a so-called symplectic basis here. We chose a symplectic basis. Symplectic basis here. So symplectic basis is the basis that satisfies the following properties. So we call them A1, A2, AG, and the other one was B1, B2, BG. Yes, B2, BG. And they satisfy the following properties. First of all, AI dot AJ is equal to BI dot BJ is equal to 0. This is for all I and J. And then AI dot BJ is equal to delta IJ. This is called symplectic basis. So the intuition again behind these basis is the following. So we have a picture like this for the surface. G holds like that. So for AI, we just choose these cycles. with a given orientation. So orientation is important. We have to pick the orientation. And so this is like A1. And for this, for the other one, we just choose going the other way around. This is B1 with this orientation. And you see that A1, B1 is equal to, in this case, there's only one intersection. And this one intersection, in fact, has positive sign because A1, B1, the orientation defined by A1, B1 is indeed the same orientation as the surface orientation at that point. So it's compatible with the given orientation. But if you choose B1, A1, the orientation of this and that, the pair B1, the tangent space at that point, and A1, they have an opposite orientation. So that's going to be -1. And so we just choose these cycles around all these points, all these kind of at these points. So this is like A2, right? And this is B2, and so on. So it's clear that AI, AJ is equal to 0 because these guys don't intersect each other. I mean, if you want, you can intersect them, but you won't get any non-zero pairing because they cancel each other if you do that. But it's better to just say that we just choose it like that and then just, okay. So such bases always exist, and this is called symplectic basis in analogy with symplectic vector spaces, which is and for symplectic vector spaces, you have this thing going to the field, for example, it's alternating, it's non-degenerate, antisymmetric bilinear form on the vector space, and that's it. That's your symplectic vector space. Okay. So then, what we did with that? Oh, yeah. So now, I talked also a little bit about Poincare dual. So then we just chose one forms. So let's see how I call them. I call them, I believe, alpha I and beta J. Yeah. Choose the one forms alpha 1, alpha G, beta 1, beta G, belonging to omega 1 of X. Yeah, C. So these are one forms. So these are Poincare duals to the cycles. So Poincare dual to the symplectic basis to these cycles. So what do I mean? I mean that this alpha I is Poincare dual of AI. So more precisely, basically, we mean alpha I is Poincare dual to beta I, to AJ, AI, yeah. And beta I is Poincare dual to BI. So these Poincare duals, you can actually construct them explicitly. One of the things that you can observe if you construct them explicitly is that actually you can choose the support of each of them exactly along those cycles and not very far from the cycle. So that's always possible to arrange. So then, let me put it this way. We can arrange for alpha I, for one form alpha I, let me emphasize. To have support in a small neighborhood of actually in a small neighborhood as small as you want. So as soon as you pick an open neighborhood around the cycles, you can arrange that support of that one form to be there in a small neighborhood of the cycle AI. And the same with beta J and BJ. Beta J and BJ. So we chose these ones. Yes. So, okay, so we need some relations between these. Okay, so let me tell you.
Sorry, Masood, are the one forms, are they smooth or holomorphic?
Oh, no, they are smooth.
Yeah,
Only smooth.
okay.
That's a good question. Yeah, no, these are smooth. This Poincare business is only in the smooth category. Of course, yeah, we won't have because actually what happens is that they form a basis for omega one, and they cannot be 2G holomorphic one forms.
Yeah,
That's
yeah.
only G. So yeah, that's a good question. Okay, so now let me just write the relations that we need, and I tell you why they are true, except one of them. Right. So basically, then what we have is the following. We have the relations. Okay. Inner product, I mean, not inner product, the pairing of alpha I, alpha J, which is by definition equal to integration over X of this two form alpha I wedge alpha J is equal to 0. Same with beta I, beta J, which is by definition nothing but integral over, this is a surface integral. You see, you form this two form beta I, wedge beta J. This is equal to 0. And then we have alpha I beta J is equal to delta IJ. So we have these three relations. So let me motivate this, let me recall so similar to intersection pairing before. On H1 XZ on singular homology. So we have a pairing on in the wrong cohomology. We have the pairing on the wrong groups. So this Durand group is H1 Durand of X with complex coefficients. Actually, we always work with complex coefficients. So this is which is the closed one forms by definition divided by exact one forms. And of course, in this case, we know that this is isomorphic to C to the power 2G. You see, this is exactly like complexification of these singular homology. It goes hand in hand with that. So there is this pairing here, which is like this, H1 Durand of XC plus H1 Durand of XC goes to C. And this time is exactly what I just chose. I just wrote over there, alpha, beta. If you want to be careful, you have to write classes of alpha and beta, but that's fine. This is just integration after you take wedge product. Okay. So this we denote by, here I denoted by maybe this notation, I don't know, alpha, beta. It's just a complex number. And similar to singular homology, this is also a antisymmetry. In this case, it turns out to be is a non-degenerate antisymmetric bilinear pairing. So can you tell me why this is non-degenerate? Oh, I mean, not non-degeneracy. Why this is antisymmetric?
Because alpha wedge beta is equal to minus beta wedge alpha.
In this case, being antisymmetric is completely transparent. It really comes from this wedge product property. So this product on the Durham cohomology level is much more transparent than the intersection pairing, which is it needs intuition and some more algebraic work if you want to be absolutely precise. But this is very, very straightforward. So this is antisymmetric. So basically, if it is non-degenerate antisymmetric, it means that this is really a symplectic, complex symplectic vector space. This is a complex symplectic vector space of complex dimension 2G. And what these relations tells us is that actually this is really honest to God symplectic basis for this symplectic vector space in this case. So the other one was only a free abelian group, but this is really a vector space over C, and that's what it is. Okay, so let me tell you a proof about the proof of this, how to prove this. Any questions? That clear? Okay, let me indicate the proof of some of these at least. Okay, so the proof. Okay, so let's call this equation 1, 2, 3. So proof of 1. Okay, so why this is true? By the way, I described the construction of these one forms alpha I. Alpha I is, you see, alpha I, remember, is point gradual to AI. Why we can use more or less this information to prove 1?
AI dot HA is equal to 0.
Sorry?
AI dot HA is equal to 0.
What is AI?
Alpha is the point gradual to AI. AI
Yeah.
was the
Yeah. So you mean it follows from that?
Right.
Yeah, that's true, but how? We want to see how. Yeah, and remember I told that we can choose alpha I actually to have support very close to just very close to AI, cycle AI, right? So since we can choose support of, alpha I. Let's not confuse alpha I with AI. These are geometric cycles. These are one forms, right? They're very different type of object. Only Poincare do all of that. Since we can choose near AI in open neighborhood near AI, and if you look at this picture that we had, for example, so this is AI, this is A1, right? And I can choose a small tubular, for example, neighborhood around this, so that this alpha I only exists here. For example, alpha 1 only exists here, right? I mean, this is A1. But then this is A2. A2 is here, it's far apart, right? So A2 has support here. And I can choose support of alpha 2 to be near A2, so it's here. So we can pick alpha 1 and alpha 2 and alpha G such that their supports are actually disjoint. So can pick alpha 1, alpha 2, alpha G such that the support is disjoint. So if you have two bond forms whose supports are disjoint, if you take the wedge product, what happens to the wedge product? It's actually identically equal to 0. You see, here this guy has support only on this, the other one has support only on somewhere else, right? When you take the wedge product, when you apply two vectors, either this is 0 or the other one is 0. So the wedge product has to be 0. Okay. So this is straightforward for all I and j.
What about if I is equal to j?
Or if I is equal to j, yeah, okay, good. Well, what happens if, that's right. What happens if I is equal to j? What happens?
Perturb one a little bit, then you get the transverse. Just like
You don't even have to perturb. What is a one-form wedge with itself? Alpha wedge alpha is 0. Because the wedge product is antisymmetric, we know, but up to sign is a graded antisymmetric product. So for one forms, alpha wedge beta is equal to minus. So that's okay. So yeah, so in a way, this is the kind of algebraic analog of that perturbation argument that you're using for cycles we were using. This we don't need to do that kind of argument. This is a straightforward. Good question, huh?
This will be true even if the Riemann surface is not compact. No?
Or not compact. I'm scared of non-compact surfaces. I don't want to be there. No, I don't want to be on a non-compact Riemann surface because there may be a huge force throw me into the infinity and then I'll vanish at infinity. I don't want to vanish at infinity. Okay, so yeah, we can think about that, but that's let's the most beautiful theories are on compact objects anyhow, so we know that. Okay, so this is the case. So and then the argument for 2 is similar, exactly similar, but there are these other cycles. So similar argument. For 2. Now 3. 3, it's most of the 3 is also obvious. So again, so let me write it here. Most of 3 is similar, namely alpha I beta j is actually equal to 0 for I different from j, since alpha I base beta j again is equal to 0 if I is different from j. right? Again, this guy has support here, the other one has support this level, the horizontal ones have supports in somewhere else. So we can always arrange that. The only thing that gives us difficulty is when I is equal to j. So, but not so if I is equal to j. So in other words, we want so basically we want to see why alpha I and beta I is equal to 1. Right? Because in this case, you have the other one, like here is, for example, beta 1 has support here. So their supports definitely intersect. So there you have the support like this. So basically you have like a band here, and then there is here, and here there is a support intersection. So that gives us, but the trick is you can use Stokes formula to prove it, to prove the identity, prove that this is equal to 1 in this case. So I won't give the proof because, I mean, it's not difficult, but I have to write some details. So I just refer you to, I mean, there is a proof, I believe, in Miranda also, but I mean, that book of Fulton I mentioned has a very transparent, nice proof, actually, you can read. Okay, so for this one, see the proof. So this is a star. The proof of a star in Fulton, if you want. It's a few line argument, but okay, so I don't want to get into that now. So this is what we have. Now, this is, yeah, okay, so far, we have singular homology, and we have the wrong cohomology. So they have both intersection pairings and symplectic pairings, and we are able to choose basis in one with nice property, and then we choose the dual basis or Poincare dual basis on the level of one form. These have similar properties. Now, using this, you can prove some beautiful relations that are needed in the proof of Riemann bilinear relations. Let me write this. So I'm going to erase this now. Yeah. Okay, so yeah, so there are some corollaries I can take. So corollary 1, for example, for any closed one form, omega 1x, we have integral, I mean, basically pairing of alpha I and omega, which is by definition the double integral of, okay, so let me write this statement. This is equal to integral of omega over aj, and integral, and the pairing between beta j and omega is equal to integral of omega over bj. So where, of course, as before, so these A1, AJ, and BJ, J from 1 to G, is a symplectic basis for H1 singular homology Z. Now, proof. Now, if you write the definition of both sides, you notice that this is quite a strange non-obvious fact, because this one is a double integral and this one is a line integral. So we are reducing a double integral to line integral now. So this, remember, alpha I and omega, by definition, is nothing but integral alpha I wedge omega, right? This is a double integral because this is the pairing on the Poincare on the Drum cohomology, right, over x. Now you're saying that you all of a sudden you can get rid of this double integral, right, by line integral of one form over the cycle AJ. Okay, so this is not obvious, right? So now to prove the first part, so we just use the fact that now this Poincare duals form a basis for omega 1 for a smooth omega 1. Use the fact that so this so yeah, alpha okay, so alpha I don't know, I forgot about up and down completely, but we don't care that much about up and down indices here anyhow. So we have got alpha I and beta J from 1 to G is a basis for omega 1 x. I mean, so for actually for the wrong, for H1 the wrong of x and c. So in other words, we can write this omega, which is a closed one form in terms of linear combinations of these things. Then you just write omega as I don't know what notations I use. Maybe I just used yeah, okay, xk alpha k from 1 to G plus sigma, again, k from 1 to G, yk, beta k, right? So there are xk and yk belonging to complex numbers. Such that you can write any closed one form as linear combinations of these basis elements, okay? I mean, there is some, okay, no, we can write it like that, yeah. Okay, now what we want to do, we want to prove this relation, right? So if you sub this into, okay, so sub this I mean this relation into this equation, because we are computing integral alpha I wedge omega over x, right? And use the relations that we just proved. I mean, we proved all of them except when I is equal to j, that we did not prove. We just proved, namely, these relations that relation, you remember, it goes like integral alpha I wedge alpha j is equal to integral over x equal to integral of beta I wedge beta j is equal to 0, and integral of alpha I wedge beta j equal to delta ij. You can sub these things into this, and then everything cancels except one term remains, and that term is what you want. So And this proves star. Okay, maybe I start. So this proves the first part, this one. I mean, this is completely transparent argument here, and this proves. Okay, so maybe I'll call this one. I'll call this two. But I mean, two is completely similar. It's the same thing. Proves one, and two is similar. Okay.
Excuse me, is it not enough to know that alpha lives in the small neighborhood of AI?
I'm just using those, yeah.
Is it not enough to show the first statement?
Which statement?
Like this, the first statement,
No,
like the
but-
first equation. It's basically you saying that your one form, you just take an integral in the small neighborhood.
Yeah.
And then you have like that alpha is equal to.
No, but I mean, you still have to worry about these betas. Because we have this beta still. We don't know where is the support of beta. So you have to decompose beta in terms of those and then reduce everything into relation between alpha. Because there is beta still.
But like alpha wedge omega lives in the small neighborhood of AI, right?
Alpha wedge, yeah, but
But
that's not enough. No, that's not enough. No. We need these relations that I proved, these three relations in the previous lemma that I proved. Okay, so we have that. Question, yes.
If the first integral is over AI.
So can you speak a bit because my hearing is.
Sorry, if the first integral is over AI, first one.
This is over. Oh yeah, you're right. Thank you. Yeah. Yes. Yes. This is over AI, of course. Yeah. Thanks. Very good. Any other questions from comments? Okay. So this is correlative 1. And correlative 2 is okay. So now these are exactly in Riemann's paper. So this is something that a lot of things we did is not in Riemann's paper, but these relations, that's the way he argued actually. Of course, didn't give any details. He just wrote down. I mean, my maybe one-page argument or any book's one-page argument is just one line for him. So I just wrote a line. So correlative 2 now, let me write it. By the way, I highly recommend you look at least look at that paper once in your life to see what mathematics is. Or how it was actually back then. So okay, so correlative 2. Yeah, now for any closed one forms alpha and beta on X. Okay, so we have again the pairing between alpha beta is equal to sum j from 1 to g. Now this is integral of alpha over aj. Again, this is like a double integral. You reduce it to a line integral, but products of line integrals. It's like calculus mistakes students do. You know, you just write. You assume students usually assume functions of function of two variables, product of two functions of one variable, and you just integrate on this factor, integrate on that factor, and then that's not necessarily the case. But something similar actually happens in this case. Alpha over aj integral. This is times beta over bj minus integral beta over aj times integral alpha over bj. Proof? Okay, so I mean, this left-hand side, as I said many times today, is a double integral, right? This is the integral alpha of h beta over x. Okay, then we write, as before, let us write. Okay, so we just expand alpha in this symplectic basis that we found. I from 1 to g, xi alpha I plus sum j from 1 to g yj beta j. These are just complex numbers, right? I mean, because this is a basis, vector space basis. And then for alpha, you just write some zk alpha k from 1 to g plus sum L from 1 to g wl beta L. Yeah. So these are one form and these 4 sets of complex numbers. Then you compute alpha of h beta. So if you compute alpha of h beta, you see that there are a lot of terms that are 0. And you use antisymmetry of wedge product. The result that remains, this is equal to basically sigma I from 1 to g. You get xi wi, right? Minus sigma I from 1 to g I from 1 to g again. This is yk zk. Ooh. Okay, that's not very good. Okay, no, no. Okay. No. Okay. Hmm. Hmm. No, that cannot be a number.
Second one be beta.
What's that?
The first one's alpha, shouldn't the second one be beta?
Oh, this is beta for sure. Yes, that's beta. This is beta. We have alpha, beta, again alpha, beta. But I don't get. So, yeah. You see, yeah. I mean, xi and wi, it should be alpha I, then beta I. They should be here alpha I, beta I. Yeah. So let me write it. This is, you see, it's just a question of taking wedge product of alpha and beta. You see, there's alpha I, beta I remains here. The other one terms cancel. So this is alpha I, wedge beta I. And then, yeah, because I need a two form, and because this is a two form, I haven't integrated yet. And then it's a simple thing using previous results, but we have to be a little careful. That's it. And then yk zk. Yk zk. There is beta k. Yeah, what is beta k? Wedge alpha k. Yeah. And then using the previous, using corollary 1, okay, so you can reduce this to what you wanted to do. Using corollary 1. you conclude that integral of okay, so then you write it like this alpha is equal to integral of alpha which is over x. So you have to integrate this. And then you can write it, you can use the previous corollary, and then this turns out to be equal to some okay, so my notation here is yeah, j from that's what I wrote, j from 1 to g integral of alpha over aj integral of beta over bj minus integral, because these are xi and wi, and the other ones are yk and bk and zk, yeah, minus integral of beta aj. I mean, these are products of numbers now, bj alpha. Yeah. Okay. Okay. So this is what we need now to prove finally these Riemann bilinear relations, but using a little more extra information that actually I proved in the last lecture, but I will recall them. Okay, now let's refresh our notation a little bit. So, I mean, the notation that we have, we call this omega of x was our notation for a space of holomorphic one form. Now we are holomorphic. So this is the space of holomorphic one forms. Of course, I mean, these holomorphic bound forms, they are closed. They are inside Z1 theorem of X. They are closed bound forms. In fact, I mentioned last time they are even harmonic with respect to some appropriate Riemann metric here. So even harmonic. So, okay, they are closed and in fact harmonic. But we discussed this a little bit, but we'll carry on further today, but a little later. But okay, so what is it? So what we showed is that so this lemma we proved actually. One was that so basically what we showed was that this is something really drastic now. Integral of, so basically pairing of alpha and beta, which is by definition integral of alpha wedge beta over x. This is actually, so what I want to say. Is equal to 0 for all alpha and beta belonging to omega of x. So this is really remarkable, right? Because if you have two holomorphic one forms and you take their pairings, according to formula that I was using today, pairing 0 for holomorphic one forms. So in this symplectic vector space, you know that this omega is, what's it called? Isn't this isotropic subspace or something? That inner product of anything with itself, and any two things are actually 0. Because it's quite possible that you have two non-zero vectors whose inner product are 0. I mean, with itself also is 0. So that's quite possible. So it's sitting, so it means that this omega x is sitting inside Z1 and in fact inside the Durham group it has a particular place with respect to the symplectic structure. So this one. Second one, what we proved is that if alpha is actually different from 0, then I times inner product of alpha, I mean, not inner product, intersection pairing of alpha and alpha bar is positive, strictly positive. Yeah, you see. So I is, of course, is complex imaginary, and this is, I mean, the proof of 1, so let's recall the proof. 1 was quite easy. What was the proof of 1? Do you remember? How did we prove 1 and 2? They were quite straightforward, basically, if you know what objects you are looking at.
But why don't you just compute it, right? Basically.
Exactly, we just write. Okay, so we just say locally, let us locally write. Because this is a holomorphic one form, I can write alpha as f of z dz, right? And beta is locally, again, in some local coordinate system around any point, is g of z dz. So actually, this wedge product is 0 even. So that's so this is the best way an integral can be 0. The integrand is 0. So this is it's very drastic. Yeah. So alpha wedge beta is equal to. So that's for holomorphic ones, but this here is different. This is holomorphic and anti-holomorphic. But this is also not difficult if you use again a holomorphic coordinate system. So let me just recall again proof of 2. Again, locally in a holomorphic chart, you can write alpha equal to f of z dz and beta, oh, not beta, actually alpha bar, if f of z bar dz bar. But this alpha is equal to so if you write down this expression I dot alpha wedge alpha bar again locally is going to be of the form I dot, so I just write f of z times bar. I mean dz is notation for dx plus I dy, and this is f of z bar. This is dx minus I dy. So this is equal to I times absolute value of f of z squared. Right? Okay, now dx wedge dx is 0. Dx wedge dy is equal to minus dy wedge dx, but there's a factor of I, right? So there is here I2, but minus 1. So this is equal to dx wedge dy. Let me write it. Oh, okay. So no. So there is minus I dx wedge dy. Again, there is minus I dx wedge dy. Okay, nice. So I2 is minus 1, but there is minus, so this is equal to 2 times. 2 is a positive number, that's important. Absolute value of f of z squared dx wedge dy. So this dx wedge dy is, of course, the Lebesgue measure on the plane, or in the complex plane. I mean, now, if this alpha is is non-zero at one point, then it is non-zero in the neighborhood of a point, and this integral becomes non-zero at that point, and at other places, it's non-negative anyhow. So this is going to be strictly positive. So that was the argument, right? So, yes. So here follows that integral of alpha wedge alpha bar I times this is strictly positive if alpha is a non-zero holomorphic one form. So we have this now, which is pretty good. Okay, now we can prove actually quite easily now because we have all the elements in place. Riemann bilinear relations. Riemann bilinear. This is very important. Okay. So it has two parts that go hand in hand with these two parts of this previous corollary. It has two parts that are consequences of these two things. So the first part is, yeah, for any two holomorphic one forms. So I just choose not just use a different notation. Part one for any holomorphic one forms omega and eta. I just use alpha and beta as before, not omega. We have sigma j from 1 to g integral omega over aj integral of eta over bj. It's really the same thing. We just wrote x minus y equal to 0 as x equal to y. That's what we are doing. That's nothing. Omega over aj, not omega, alpha over aj, beta over bj is equal to, you just change the orders, j from 1 to g, integral beta, yes, over aj, integral alpha over bj. It's a certain symmetry condition. Okay. I mean, this follows from the part corollary one, which is, I mean, from part one of corollary two. Okay. So follows from part one of corollary two. Yeah. Obviously, yeah. And obviously now the second part, which is this positivity statement, also has interpretation in terms of this. I mean, it's really corollary two is real Riemann bilinear relations. I don't even have to write it this way, but let me write it anyhow. Okay. Now, two is that if alpha is different from 0 is a holomorphic one form, non-zero holomorphic one form, then okay, sigma j from 1 to g integral of alpha over aj, yes, times integral beta, okay, alpha bar over bj minus integral of alpha bar over aj times integral of alpha over bj, and if you multiply by I, everything here, this is a strictly positive. I mean, this follows from part two of corollary two. It's the same thing, really. Yeah. Just wrote it this way. Okay, so let me say something after I wrote. So this is follows from part two. Yeah. So to prove this thing so far, what we had to do we have to choose a symplectic basis for H1. We chose a dual one for the Rom cohomology. And then we picked basically the dual basis to be Poincare dual. And then we just did calculations and these two things. But the question is why on earth one would be interested in these strange relations, because where they come from, what is the motivation for them and these things. It looks completely unmotivated to look at such formulas or even think about such formulas. Now what I want to say is that, or actually I want to show is that actually these things are suggested by these period pairings that I define. And one of the consequences of this is that this period lattice is a lattice of full rank, of rank 2G in omega x, actually in omega x star. And it basically shows that that lattice is in the Siegel upper half plane, as I will discuss now. I will discuss. So it's a very particular type of lattice that sits in the complex plane CG, complex space CG, which is R2G. Okay. Okay, I think now it's a good time to stop, and then we take a quick break, maybe 5 minutes, and then we continue. Okay. Yeah. Any questions?